Good morning, guys. Today we're going to look at solving linear systems using matrices using a technique called Gauss-Jordan Elimination. The way Gauss-Jordan Elimination works is first we take a system, write it as an augmented matrix. That means we write our coefficient matrix. Augment means to add on or increase. So we take our coefficient matrix, we add our constant matrix onto the end of it. So labeling it X column, Y column, K for constant, because we're already using C for something else. So we're going to take this coefficient matrix, or with the constant matrix added on, this augmented matrix for our system. Really, we're just dumping the variables in the plus and minus, and the addition symbols. Minuses would be in there as negatives. We're going to perform what we call elementary row operations on it until we get this. This should look very familiar. What this is our identity matrix, and then on the left side where the coefficient matrix was, and then some new values, could be the same values, I don't know, but some values on the right side where our constants were at. And it's very important how we read this, because this says AX plus BY equals C. DX plus EY equals F. So when we get to this right here, get to this identity matrix, what is it we have? 1x plus no y's will equal m. So this tells me x equals this number right here. 0 x's plus 1y is equal to n. Y is equal to this n value right here. So after I've performed these elementary row operations, reading this, the right column is my x and then my y. That's the order I happen to have written my coefficients in the beginning. Now, what are elementary row operations? Well, right here we have our elementary row operations. First thing I can do is swap two rows around. That should make sense because they're just systems of equations. Can I swap systems of equations and still have the same system? Yeah. So we could swap two rows around. Can I multiply a row by a scalar? Well, a row is just a line. Can I multiply a line, both sides of the line, by a scalar? Can I make this line twice as long and have the same line? Or can I make this line half as short and have the same line? Yes, I can multiply a line by a scalar, so I can multiply a row by a scalar. And finally, I can add a multiple of one row to another row. Very important thing there. Back in systems of equations, can I multiply one row by a value and then combine that new row with an existing row? And the answer is yes, because that's the premise behind linear combination or the elimination technique in our algebraic work. So what we're doing is we're taking all this stuff that we did algebraically and we're keeping it in matrix form so that we can impact our constants as we go through and solve it entry by entry to get the identity matrix on the left side. Works for 2 variable systems, 3 variable systems, 4 variable systems. It doesn't matter. Actually, the larger the system, the better it is because the steps, the process is going to be the same, but it's a lot cleaner and neater than other types of strategies such as your algebraic techniques or your inverse matrices or Kramer's rule. So this ends up being the best strategy, I feel, as we get into large systems of equations, many variable systems of equations. So give me a second, I'll get a couple examples and I will kind of talk you through how these elementary row operations will solve a linear system. So here we have an example. I've already set it up as an augmented matrix. 2, 1 were my x coefficients, 7, 3 were my y coefficients, negative 53, negative 22 were my constants. So we're going to go through the elementary row operations. You can pick any one to use at any time. First thing you need to know is I need to focus on my ones. Get the 1 for each column first, then you work on getting the zeros for the identity matrix. So let's look at this one. First thing I'm going to look at is, do I have a 1 in that column to begin with? In this specific problem, yes. First column has a 1 in it. I'm always worried about this top left corner. I'm going to take column 1, then column 2, then column 3, and so on, however many columns there are. So focusing on column 1, I've got to get a 1 into this top position, into this identity position, because remember what you're working towards. I am trying to get 1, 0, 0, 1, and then some numbers. So I've got to get a 1 in that position first. If I can do that by a row swap, do a row swap. That's always the best way because there's not any calculations. You're just flipping 2 rows. So what we're going to do is swap, and we always label this so we know what we've done if we need to go back and check or just to keep track of things. I'm going to swap row 1 and row 2. Let's try to make that look like an R. Swap row 1 and row 2. So here I go over here. 1, 3, negative 22, the whole row. 2, 7, negative 53. So I just swapped row 1 and row 2. The next step is finish out the zeros for the column. I need this to be a 0. Okay? That's where the linear combination stuff comes in. Right? If we want to eliminate a variable, we multiply one equation by a number to get opposite coefficients. That's what we're doing. We're going to use that third elementary row operations. I'm going to take a multiple of row 1 and combine it with row 2. Well, if row 1 is a 1, we call that the pivot. That's why we always identify our 1s first. I just have to take the opposite of this number I want to get rid of. So I'm going to take negative 2. Oh, let's get rid of this. I'm going to take negative 2 times row 1 and add that to row 2. Negative 2 times row 1 and add that to row 2. And it's very important that we recognize that that will not change row 1. That will just produce a new row 2. Because we don't want to change row 1. I want to leave that as a 1 because that's what I'm trying to get, that 1 in that position. So let's look at what happens when we do that. Negative 2 times row 1. Well, negative 2 times 1 is negative 2. Negative 2 times 3 is negative 6. Negative 2 times negative 22 is positive 44. And then I'm going to combine it with row 2. So let's go to our next step. We know that row 1 we're not changing, so let's leave it alone. Now we want to combine to get a new row 2. Negative 2 plus 2 is 0. Got the 0 that we're trying to work towards. Okay, negative 6 times 7 is 1. Heck, we've got the 1 that we're trying to work towards. And then 44 and negative 53 is what? Negative 9. So we've taken care of getting a 0 right here, and we actually have our new pivot, our second column pivot, at 1. So negative 2 times row 1, combine that with row 2, gives us a new row 2. So row 1 stays the same. Now we want to work on this second column. This bottom number needed to be a 1. If it had still been a number like a 2, I'd have just multiplied the whole row by 1/2. Because 0 times a half would have stayed 0. It wouldn't have affected anything. The 2 times a half would have given me a 1, which is what we want. So there are 2 ways to get a 1 where you need one. First way is a row swap. The other way is multiplying by the reciprocal of that number. So that's always, once you finish out one column, you've got to identify where your pivot is in the next column, where your 1 needs to be, and then you just get that by multiplying by the reciprocal of that number, that whole row by it. But we have the 1 we need, so we just need to finish off right here. How was it that we get a 0? We do the pivot for that one, for that column, times the opposite of what we're trying to get rid of. So I'm going to do negative 3 times row 2. negative 3 times this row, and then combine it with row 1. Or you say, well, wait a second, if I combine stuff with row 1, won't that mess up my 1? No, because what am I adding to my 1? 0. That's why we take care of one column at a time. And this will give me a new row 1. So we go through, we do our math, do our arithmetic. Negative 3 times 0 is 0. Negative 3 times 1 is negative 3. Negative 3 times negative 9 is positive 27. And when we check it out, 1 plus 0 is 1. Bottom row stays the same. 0, 1, negative 9. Okay? 0 plus 1 is 1. Negative 3 plus 0 is 0. Negative 2 plus 27 is 5. And remember, like we talked before, 1x equals 5, right? And 1y equals negative 9. If you need to see that back in this form right here, just step back for a minute and write it back as a matrix. I've got 1x plus 0y equals 5. I've got 0x plus 1y equals negative 9. So what's the solution to the system? That's 0, x equals 5, y equals 9. So we just took this system in matrix form, put it back in this form, and we've got our solution. But if you recognize it, that's my x column, that's my y column, so x is 5, y is negative 9. Very fast way to do it if you're real quick with your calculations. It's phenomenal when you look at it for large systems, large variable systems. So if you'll give me a second, I will get another example up here and let you play around with it yourself. Okay, here you go, guys. A 3-variable system, and I want you to pause this video and take a few minutes, solve that system using Gauss-Jordan elimination. Get yourself a big clean sheet of paper because it's going to take you a little bit of space, but I don't know if you're like me, you'll actually enjoy it a little bit. So pause this and take yourself a couple minutes to work on it. Okay, guys, hopefully you were able to get a solution. Let's go through, check your work, and see how you did. All right, as you can see, I've already got it set up as an augmented matrix. Hopefully I've got enough room to get them all in here, but we'll just take it as we go. First thing I do is I need to get a 1 in that pivot on that first column. I always like to write down what I'm headed to until I get familiar with the identity matrices to know the 3-variable system. The 3x3 identity will have that look to it. So that's where I'm headed, so I need a 1 in this top left. 2 ways I can do it. One is to just divide this 4 by 1, multiply by 1/4, and I can get a 1. Or I could swap this 1 I could swap rows 1 and 3 to move that negative 1 up. I'm not going to do a swap in this case because it's not a 1. It's a negative 1. And to change it, I'd have to do the swap and then multiply everything by negative 1. Well, if I'm going to multiply, then I might as well just multiply and make everything 1/4. Just to give you a heads up though, guys, there are going to be fractions that pop up through here, especially when you start multiplying by fractions, multiplying by reciprocals of values to get your pivot points, your pivots, your 1s. So the fractions will just tag along, just do the work with them and you'll be okay. So that's where I'm going to start out. I'm going to multiply row 1 by 1/4. So I'm going to do a 1/4 of row 1 to get a new row 1. So when I do that, so if I get a couple of them in here, rows 2 and 3 don't change. I haven't touched them. So 2, 2, 4, 1, negative 1, negative 1, 1, negative 5. I always like to write down what I'm not touching so it's done and I don't accidentally mess with it later. So a 1/4 of row 1. A 1/4 of 4 is 1. That's the pivot we're talking about. That's what we're going to work everything else in that column off of. A 1/4 of 1 is 1/4. A 1/4 of 6 is 3/2. And a 1/4 of negative 4 is negative 1. Now we're on our way. Next thing I do, I got to wipe out this column. I've got to get zeros. Well, we already talked. We do that by the multiplying by or adding a multiple of another line. So if I want to get rid of this value right here, I can do -2 times row 1 and combine that with row 2. This is your pivot, so I'm always going to multiply the opposite of what I'm getting rid of. So I've got a 1 here, so if I do -2 times this, add it to that 2, I should get my 0. That'll give me a new row 2. So if we do that, row 1 won't change. Row 3 won't change. It's only row 2 that's going to change. So let's look at our new row 1. Give yourself a little room. So -2, -0.5, -3, +2. That's my temporary row 1. -2, +2 makes 0. We're adding them up. Well, -0.5 and 2 is 3/2. -3 and 4 is 1. And 2 and 1 is 3. So that's our new row 2. Now we need to get the 0 for row 3 right here. Well, I already have opposite numbers there, so I don't even have to do a multiple. I can just add those rows together. So I'm going to just add row 1 and row 3 to get a new row 3. I don't care about row 1. I don't want to change it. We're just going to add a multiple. The multiple happens to be 1. So as we move up here, see if we got enough room to do this. Row 3, I'll write that down here. Row 1 plus row 3 to get a new row 3. So row 1 stays the same. 1, Z, and ahead of myself. 1, 1/4, 3/2, and -1. Row 2 stays the same. 0, 3/2, 1, and 3. And we'll get a new row 3 just by adding them up. 1 plus -1 is 0. 1/4 and -1 is -3/4. 3/2 and 1 is 5/2. -1 and -5 is -6. So you just have to kind of work with these fractions and live with them. They'll shake themselves out in the end if the system is neat, has a nice, neat solution. All right, so we have finished row 1. Everything's good, right? Or column 1. Now we move to column 2. What's the pivot? The pivot is this middle. We need a 1 in the middle row. So we get that by multiplying by the reciprocal of that. So I'm going to multiply 2/3 times row 2 to get a new row 2. So row 1, not affected. 1, 1/4, 3/2, -1. Row 2 or row 3 not affected. 0, -3/4, 5/2, and -6. It's just my row 2. Well, 2/3 of 0 is 0. See how our first column was not impacted? 2/3 times 3/2 is 1. Now we have that pivot to work off of in column 2. And 2/3 times 1 is 2/3. 2/3 times 3 is 2. Yes. So we go through and we have our new pivot. Now let's try to get rid of column 1, or this entry up here. So if I want to get rid of it, I got to multiply row 2, my pivot row, off of, by the opposite of it. So -1/4 times row 2 combined with row 1. The opposite of 1/4 times this row combined with row 1. So we go through. So row 1 will change, so row 2 not going to change. 0, 1, 2/3, and 2. 0, -3/4, 5/2, and -6. And what's our new our temporary row 2 going to look like? So -1/4 of row 2. So -1/4 times that is 0. -1/4. What's that? I just went brain dead. 2, 1/6. And then -1/4 of that is -1/2. All right, so that's our temporary. Add them up, 0 and 1 is 0. Didn't impact column 1, or didn't change column 1 there. Negative 1/4 and 1/4 is 0. 1/6 and 3/2, so 1/6 and 9/6 is 8/6. 8/6 is 4/3. Hopefully my arithmetic is correct there. And then negative 3/2. We'll know here in a couple minutes. Okay, let's do the same thing to get a 0 in this position. So I'm going to do the opposite of negative 3/4, which is positive 3/4, times my pivot row, row 2, and combine that with row 3 to get a new row 3. So we go and row 1, not changed, 1, 0, 4/3 and negative 3/2. Row 2, not changed, 0, 1, 2/3 and 2. Row 3, we need to get our temporary row 2. So 3/4 times 0 is 0. 3/4 times 1 is 3/4. 3/4 times 2/3 is a half. And 3/4 times 2 is 3/2. Correct? 2 or 4, yeah, 3/2. Combine. 0 and 0 is 0. Negative 3/4, positive 3/4 is 0. 5/2 and 1/2 is 3. Negative 6 and 3/2 is 6, 12, negative 9/2. Okay, so we can see it's starting to clean up a little bit as far as all those fractions are concerned. Column 2 is finished. Now we move to column 3, and our pivot in column 3 is our row 3 number. I need that to be a 1. We've already talked about this. How do I turn a value into how do I turn a single value into a 1? I multiply by its reciprocal. So I'm going to multiply row 3 by 1/3, because 1/3 times 3 will give us 1. All right, so row 1 didn't change. 1, 0, 4/3, negative 3/2. 0, 1, 2/3, and 2. And then the row 3, 1/3 of 0 is 0, 1/3 of 0 is 0, 1/3 of 3 is 1, 1/3 of negative 9/2 is negative 3/2. So we actually know what z is. 1z, 0x is 0y, 0 and 1, 0x is 0y, and 1z equals negative 3/2. If you wanted to, realistically, you could stop right there and start doing substitutions. If z is negative 3/2, 1y plus 2/3 of z, you could do 2/3 and then substitute negative 3/2 in to get your y. Then you could take your x and your y, plug them back in to get your z. So could stop right there, but we don't want to do that. We're having too much fun. So we've got our pivot for the third column. Now let's finish this thing off by getting zeros in the other two. So here we go. Let's just start at the top. To get rid of 4/3, I do the opposite of 4/3 times the pivot row plus row 1. Okay, so we didn't touch. So row 1 is changing. So row 2, 0, 1, 2/3, 2. Row 3, 0, 0, 1, negative 3/2. They didn't change. Let's get our temporary row 3 up here. 4/3 of 0 is 0. Negative 4/3 of 0 is 0. Negative 4/3 of 1 is negative 4/3. Negative 4/3 and negative, just went brain dead, 3/2. 3, 3 cancel. 4 and 2 is 2. So 2. Yes. So add them up. 0 plus 1 is 1. 0 plus 0 is 0. Negative 4/3, positive 4/3 is 0. 2 minus 3/2 is a half. So we've solved for x. X is a half. Solve for z. Z is negative 3/2. Now we just finish off to get y. So to get rid of that 2/3, I do the opposite times my pivot row plus row 2 to get my new row 2. Well, we know row 1 isn't going to change, 1/2. Row 3 isn't going to change, -3/2. Let's put a temporary row 3 on here, so we combine it with row 2. So -2/3 of 0 is 0, -2/3 of 0 is 0, -2/3 of 1 is -2/3, and -2/3 times -3/2 is +1. And we add them up. 0 and 1 is 0. Sorry, 0, 0 is 0. 0 and 1 is 1. -2/3, +2/3 is 0. 1 and 2 is 3. So just like before, we can see that 1x equals 1/2, 1y equals 3, and 1z equals -3/2. So we have our linear system solved in, I don't know what we have, 9 easy steps. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10 if we count that there on the end where we wrote it down. So, really easy. I think it's, I really enjoy doing Gaussian elimination because I feel like it's kind of first time you start looking like you're doing big kid math. But that's Gaussian elimination to solve systems, Gauss-Jordan elimination, because we went all the way through to the full identity matrix. Gaussian elimination stops with just the zeros on the bottom, and then they do substitution. But Gauss-Jordan, we go all the way to get it all the way to the identity matrix on the left-hand side. One special case that I do want to put up here for us to look at real quick, so let me get that up there, and then we'll talk about it. So hold on one second. So guys, here's this last example I want to look at. Let's quickly go through. We're doing a 2-variable system because we can see more than enough from that. Let's go through and let's do the elementary row operations. Let's do Gauss-Jordan elimination to solve this system. First thing, get a pivot. Get a 1 in that first position, so we do half of row 1 gives us a new row 1. So half of 2 is 1, half of -4 is -2, half of 9 is 9/2. Okay, 3, -6, 6 won't change. Now we want to get 0 down here. Let's go back over here. So I'm going to do -3 times row 1, opposite of your pivot row, plus the row you want to change to get a new one. So 1, -2, 9/2 doesn't change. Let's look at it. -3 times 1 is -3. -3 times -2 is 6. -3 times 9/2 is what? -27/2. So when I combine them together, boom, boom, boom. 3 and -3 is 0, which is what we want. -6 and 6 is also 0. And 6 minus 27/2, so 12 minus 27 is -15/2. At this point, we have an issue. We've got our first column taken care of. We've got 1, 0, but we need a pivot. We need a 1 on the second row because that needs to be our pivot row for this column too. Problem is, there's no way to get a 1 right here. Only way I could get a 1 right here would be to divide this by -1/2, right? And I could be that a 1 and then swap it, but then I've changed this position, or this pivot now. So we need a 1 here. There's no way we can get a 1 here because it's not a number, it's a 0. Okay? And I can only change a number to be a 1 by either adding it to something, which we don't want to do because we know it would change this one, or multiplying it by its reciprocal. Well, 0 doesn't have a reciprocal, so we can't multiply it by it to get 1. At this point, do a little analysis. This says 0x plus 0y's equal -15/2. Is 0 ever equal to -15/2? The answer is no. Just like when we had our algebraic technique and the variables would all cancel, whether it be substitution or linear combination, and we got a false statement, 0 equals 15/2, as we have, or -15/2 like we have here. We knew it was no solution because there's no combination of x's and y's that will ever make 0 equal -15/2. Do a little closer inspection. 1 to 2, correct? For my ratio, 1 to 2, or 1 to negative 2, 1 to negative 2. So we can see these would have the same slope, but 9 to 4, or 4 to 9, and 6 to 6 are not the same ratio, so they wouldn't have the same y-intercepts. Same slopes, different y-intercepts would be parallel lines, which is no solutions. If I was going to get an infinitely many solution scenario, say I switch this 6 and 9, and we've got a 4 to 6, which is 2 to 3, and a 6 to 9, which is also 2 to 3, that would be infinitely many solutions. But what infinitely many solutions looks like is just like on your linear combination problems, when you get your variables cancel out and your constants cancel. 0 is equals 0 is always true, so there's infinitely many combinations of x and y to make that be true. So as you're going through and you're doing your elementary row operations, if you get a whole row that just completely wipes out, and it could appear at any time or any place, especially when you get into your larger variable systems, whole row wipes out and you've got all zeros on the left side where your variables would be. If that's ever equal to a 0, it's infinitely many solutions. If it's ever equal to a non-zero value, then that is a no solution system. If you're not sure when it's infinitely many, when it's no solution, know that if everything wipes out and you can't go any further to solve, just go back and do a little inspection of your original system to decide if they're parallel lines or equivalent lines. Solving systems of linear equations using Gauss-Jordan elimination. And I will see you in class tomorrow, guys.